So, hello and welcome to either lecture 22 or the last lecture of this course, depending on where you are. Okay, so yesterday, we had these two proofs of convergence of the accelerated scheme for gradient descent. And today we're going to talk about one quite important extension of the method. Actually, the extension of the method is not any more difficult than the analysis of the accelerated scheme in general. But the extension is kind of it's practically very relevant. So we're talking today about the proximal gradient method and not the gradient method anymore. So our lecture is then 22 is the proximal gradient method. So, and here we're going to use or see one of the important things, you see the importance here of the proximal mapping, proximal gradient method, and acceleration. So, actually, I'm not really sure about the origin of the proximal gradient method. I guess it's pretty old. Maybe it's from the 80s already, maybe even older. So anyway, so the method is for problems with the following structure. So we not only minimize some function f over Rn, but we minimize the sum of two functions, f of x plus g of x. So this is actually not any different if you just say functions, because, well, f plus g is just any other function, but we assume that f and g are convex. Okay, that's also nothing new, and we assume that f is L smooth, but g is not. G is only lower semi-continuous, nothing more is assumed. But so what we assume, sorry, that was the other way around. So we assume that G is L smooth, and F is only lower semi-continuous, but we assume that the proximal operator of, let's say, H times F is available for some or any positive H. Let's assume for any. So with available, I mean it's simple to apply. So if when you talk about optimization and talk about steps one method can do, it's always important to think about the computational effort one step needs. So in the gradient method, we assume that evaluating the gradient is simple. Which is not always the case, actually. Some functions have gradients which are kind of difficult to evaluate, so think of backprop, for example. So here we assume that the evaluation of the proximal map of f multiplied by some positive h is, again, it's kind of comparably cheap than the evaluation of the gradient. So then we can motivate the proximal gradient method as follows. So if G is L smooth, it's also continuous everywhere. So the subgradient sum rule applies for f plus g. And we can characterize optima by saying that 0 is in the subgradient of the objective. And so what did it say? F is just subdifferentiable, but G is smooth. So subgradient sum rule says this. And now, of course, we can multiply this inclusion by some positive h and rearrange to minus h times gradient g of x star is an element of h times the subgradient of f at x star. Okay. And further, we can just add x star on both sides. If we add x star on both sides, we get x star minus h times gradient g at x star is an element of x star minus a plus h subgradient of f at x star. And remember, oh, this is here the element sign. Not remember, so but the right hand side you can express that the same way as identity plus h times subdifferential of x star. Okay. Now one thing we probably didn't talk about that explicit in the past, but what is true, and it's actually pretty simple, and maybe I just derive it now. The prox operator of h times f at some z, let's say. Remember that we defined this as the minimizer of 1 over 2, so over some y of y minus z squared plus h times f of y. And if we characterize this here, the minimizers of this, again by taking the gradient, so this says if this prox, so let's call the prox z star, then it holds that this minimum is assumed at z star, which means that 0 is in the subgradient of that guy here at z star. This again is differentiable, it has a gradient, so this gives us z star minus z, and this gives us h subgradient of f at z star. And if we have a look at this, this can be rearranged to z is in identity plus h times subgradient of f at z star, which then says kind of, and we'll come to that in the next lectures, but so just formally here for those who don't attend the next lectures, this says that z is kind of the inverse operator of that guy here. So this inclusion here, z is in the subgradient of that, characterizes z star being the proximal of f of z. So this inclusion here characterizes z star is the prox of z, and so this here, this inclusion here characterizes x star is equal to the prox of this, to the prox of hf of x star minus h gradient g of x star. So what we did is we characterized the solution of our original problem by this equality here. Okay, and so that's a nice equality here, and we see that we have a kind of gradient step with respect to the smooth function of the objective, and then followed by that we have a prox step. And note that the step size which appears in front of the gradient also appears here down in the prox. And so basically we have proven now, we've basically proven that minimizers here are actually fixed points of this operator on the right hand side. Okay, so this then motivates to use this as an iteration. As always, fixed points may be well suited for iterations to find solutions of the fixed point equations, and so here the nearest, the obvious choice would be to just do like prox of xk minus h times the gradient of g at xk. So doing a gradient step from x, applying the prox, giving us the next iterate, and iterating this. So this is the proximal gradient method. Okay, looks familiar, not that different from the gradient method, but there's this prox inside, so and this may change things. So we know that the prox is non-expansive, so it does not increase distances between points, so this seems like nice, that this has a chance to converge, but this does not really, it's not enough to prove convergence, and especially it's not really enough to prove that the method converges a certain rate. Okay, so we start the analysis of this method, and we do it in a kind of obvious, obvious, I don't know, maybe obvious reformulation. So we introduce another map which we call capital G down H, sub H of X as 1 over H, and there's a typo in the lecture notes, I already corrected just now, of, oops, there's also one parenthesis too much, I guess. Yes. So it should be 1 over H times X minus the prox of HF of X minus H times gradient of G of X. So let's do this count right. There's a parenthesis too much. Okay, so why is this a good definition here? This leads to the fact that xk plus 1 is, if I'm not mistaken, actually xk minus, that's another typo, t should be h once again, xk minus h times gh of xk. So just look at this iteration here, and then you see that these two things here are actually the same. If you just write that down, the h cancels, the x cancels, and you end up with the box here. Okay, so this is kind of, so this then very much looks like the gradient method, right? If this here would be the gradient of a function, this would be just the gradient method for something else. Okay, so but it's not, in general, it's not the gradient of something as far as I know, so we have to analyze it differently. So, okay, and we'll collect a few results which help us to prove what we want. So the first lemma is 22.1. It says if we have positive h, then we have that gh of x minus the gradient of g at x of small g is an element of the subdifferential of f at x minus h gh of x. Okay, that's the first thing. And if g is L smooth, then for h between 0 and 1 over L, we even have that you can say that g of x minus h capital G h is smaller or equal than g of x minus h. Then we have gradient of g of x. Here then have gh of x plus h over 2 norm of gh of x. So, and if you compare this to the first inequalities we analyzed when we analyzed the gradient method, this is something which looks familiar actually. So this is at least what happens to the function g after a prox step. Yes, it's smaller than g has been before, minus this linear term plus this quadratic term. And if you replace this gh by the gradient of something, maybe the gradient of small g or so, I think this is basically what we already got for gradient descent. Okay, so this is also very simple to prove. So the first thing we need is that u is the prox of something, let's say hf of x. If and only if you can, just rewriting, x minus u over h is an element of the subgradient of f at u. Okay. So and then if we use as u, if we replace u by x minus, here we go, 1 over h, yeah, x minus h gh of x, and as x we're going to use x minus h gradient g of x, then this inclusion here exactly gives that one. Sorry, I'm off screen now once again. If I use for u this guy here, x minus h times gh of x, so it's an h down here, and as for x we use x minus h times the gradient of x, and so we know by definition that this relation here is true, so this is equal to the prox of that. And if we plug both in here, we see that the x up here cancels, the h cancels, and this is exactly what we wanted. So if we call this star, then you can say this here shows star. That's already it. And for the second claim, we use, which is lemma way back, lemma 12.4, which is already, so you have it in the lecture notes. And it's just the estimate for L smooth functions, which says that g of x, the g of y minus g of x minus gradient g of x, y minus x is upper bounded from above by L over 2 x minus y squared. That's use lemma, that's lemma 12.4. And what does this give us? We use it with y equal to x minus h gh of x, and then we already got what we want actually. Yeah. Now it shows something almost. This gives us that g of x minus h gh of x smaller than g of x. So we bring this over here, plus y minus x is just minus h g of h. So we get here a plus. Why do we get a plus? I messed up the signs somehow. Oh god. Let me see. So how should it be? It goes over here. Actually, it goes over here with a plus, but y minus x gives a minus, so the minus is correct. H g of x, gradient of g of x, gh of x, and this should be like that. And of course, here we get here we get again h times gh. We get an h squared out, so we get here plus l h squared over 2 gh of x. So we could work with this, but we could also say that l h squared is of course smaller than h for h smaller than 1 over l. And then that's it. Okay. So that's nice, but that's not really what we want. So here we see that under appropriate conditions on h, this g getting smaller with the gradient step, or with the proximal gradient step, but we would like to have f plus g getting smaller. So what we now do is, so we abbreviate with capital F the full objective, small f plus small g, and then we want to formulate that even this capital F kind of gets smaller. So the lemma is 22.2. So we need f convex, L as C, G convex, and L smooth. And then we have for this f and h between 0 and 1 over L, that we have f of x minus h times gh of x, so that's the proximal step, that's smaller than f of z plus gh of x, x minus z minus h over 2 gh of x. Yeah. So that's not actually, I do not see immediately why this is helpful, but let's first prove it, and then we're going to see what we can do with it. So We use, of course, at some point the lemma 22.1, but first let's start with the left-hand side. So we start here and write this as f of the argument x minus h gh of x plus g x minus h gh of x. And here for this small g, we just proved an upper estimate in the previous lemma. So this then is bounded from above by f of the prox step. And here we get g of h minus h times gradient g, gh, and we estimate here by plus h over 2, I guess. Nothing more than that, yeah. Okay. Okay. And so that we use the that point here, but now we also use the star inequality here and write down the subgradient inequality. So this is a subgradient inclusion, so it's a characterization by an inequality. So from the blue star inequality, we get that f of z is larger or equal to f at that point here, f at the point where the subgradient is taken, plus the gradient, this subgradient, one of the subgradients, this here is one, gh of x minus gradient g of x, times z minus this, which gives us z minus this gives us z minus x plus h gh of x. So that's the subgradient inequality from the blue star inequality, and we can clean that up a little or rearrange a little by collecting. Here we get gradient squared, and I think that's more or less it. So we keep this guy here as it is, and get the gradient squared. So it's h times the gradient gh of x squared, and the rest we write as plus in a product of gh of x minus gradient g of x times z minus x, and then we missed this guy times this guy, which is minus gradient g of x and h times gh of x. So that's where we get. Okay, so but now we can use this in this inequality here. So we have this guy here on the right hand side, and we have this, and we have an upper bound. So we can, one way to see it is to bring all this to the left hand side, plug the left hand side here instead of this, and then collect and clean up. So this gives us then f of x minus h gh of x small equal then then what we get. So we get an f of z, we also get a g of x, and we get the rest, so some of the things cancel, so we get a gh of x minus gradient gh of x times x minus z. Yes, and furthermore we have minus h over 2 gh of x squared. So that's what's left after cleaning this up. And then we see that this term here, g of x minus gradient x minus z by convexity of g is upper bounded by f of z. So we get rid of this by replacing g of x by g of z. And the rest is that's left here. And that's exactly what we wanted to prove, because this here is f of z. Okay, so that inequality, I can't really see why this is good, but we'll see the next proposition now. This will be the result, which will be really helpful in the convergence proof. So, and because we're going to show a few inequalities which have been really helpful in the analysis of the gradient and accelerated gradient method. So, the same assumptions: f convex, maybe just f convex, LSC, G convex, and L smooth. Again, capital F is small f plus G, x star, well, f of x star will be called f star minimum. So there exists a minimum, it is attained at x star. We have the proximal iteration. Oh no, this was too new. Yeah, we denote here in this lemma x plus as the prox step. H f of x minus h gradient g. And we assume that the step is between 0 and 1 over L. So, and then we have four things. The first thing which is true then is for all y, we have that f of x plus 1 over 2h x plus minus y squared is smaller equal f of y plus 1 over 2 x minus y squared. And so maybe this looks familiar. We had the exact same inequality for small f here, just doing one gradient step for f. So this, because we have this the same thing here now, but for the sum of f plus g as objective, and for the prox step, we can see that probably the proximal gradient method exactly behaves almost similar to the gradient method. So a few more things which one can prove, which are more or less direct consequences. F of x plus is small equal f of x minus h over 2 gh of x squared. Third consequence is that f of x star x plus minus f star is smaller equal 1 over 2h times x minus x star squared minus x plus minus x star squared. And the last consequence, which you also can see, is that an x plus minus x star is smaller equal than x minus x star. Okay, this yeah, and we'll see this. This shows us a lot of things which we would be interested in, right? So this here shows that after the prox step we get closer to any minimizer. This shows that we have an upper bound on the distance to minimizers by these distances here to minimizers. This gives us descent of the objective. This gives us always descent of the objective up to h is 1 over L, and this all follows from the first inequality. So let's prove this. This is fairly quick. So this x plus is actually nothing else than x minus h gh of x. That was basically the definition of g of h. And then we use the previous lemma 22.2, which showed us that f of x plus smaller equal than f of y plus gh of x minus y minus h over 2 gh of x squared. What we do now here is we basically complete the square. So this is this looks like could be a square. So this is here squared. So we just need to add a multiple of this squared. Actually we have to subtract it and add it again, and then we got the square completed, and so this gives us f of y. If we do this completion of the square, we have again t has to be in h once again, 1 over 2h times x minus h gh of x minus y squared. And so what we had to add was 1 over 2h x minus y squared. So if you here split this up along this here and expand the square, and then you see that this guy cleans up, and so you arrive back there. And you see that this here is again x plus, and then that's it. That's x plus, and this shows the first inequality. So for this, for the second, we just use you just use that y as x. If you do that here, then this guy vanishes. This gets x plus minus x. X plus minus x is hgh. And this is then moves from the left to the right, and then you're done. So, and for the third, you just use y equals a star. So in 1, and here again in 1. If you use y equal x star above here, this gets f star. And this over here, and then you're already there. And finally, 4, you get 4 from 3, since f of x plus minus f star is like that, because this is the minimum value, and that's already it. Okay, so these are the important inequalities here, and probably the most important one is this, although it doesn't look like it, but just plugging in a few things, you get all these nice interesting things here and helpful things. Okay, this was pretty quick, and we're ready to state first the convergence of the standard proximal gradient method. Okay, here comes the theorem. So same assumptions as here. F convex lower semi-continuous, G convex and L smooth. This is the objective is called capital F. This is the minimum. That's the zero outer iteration is the proximal gradient iteration. And if we now fix H equal to 1 over L, one can actually prove that the objective at the kth iteration minus the optimal objective is bounded from above by L times x0 minus x star squared over 2k. So the gradient method, proximal gradient method, also converges like 1 over k, same as the gradient method. And actually, I even think the constant here is the same, which doesn't come as a surprise because the inequalities here are exactly the same. And also the proof is basically the same. But so I don't think it's bad to do the same proof twice. It's more or less the same proof. It's probably, no, actually I think it's a little different. Okay. Yeah, so what we do is we use the point 3 of the proposition 22.3, of course with x plus being xk plus 1 and x being xk. So the third point here, this guy over there. If we have that, then it's simply that f of xk plus 1 minus f star is smaller equal than the difference here. So we fixed actually h to be 1 over L, so we have now here L over 2, but still have the difference here xk minus x star squared minus xk plus 1 minus x star squared. Oops, and now now we sum up again. So it's always good to sum inequalities up if something's going to cancel, or at least you have under control what adds and subtracts in each step. So here we have the telescoping happening on the right hand side, and here we just sum everything from, let's say, 1 to k plus 1, and you end up with f of xi minus f star smaller equal to, constant remains, and the the first or the last. Actually, I think I have to start at 0. Yeah, I wanted to start at 0. So if you start at 0 here, the first one is x0 minus x star. That's good. And the last one is xk plus 1 minus x star. Okay. So now how do we proceed? So now the catch is, or the good news is that from this here, the number 2, we know that capital F is actually decreasing. So the last one here is the smallest. So and what holds the sum is always smaller than larger than the smallest thing times the number of things you add. So what we now use is f of xi is decreasing by this proposition 2. And this tells us that the last one here is the smallest. So it's smaller than the sum. No. Times f of xi minus f star. So from 0, and so the number of summons here we have is actually, now I'm confused, it's k plus 2, right? So we have 0 from 1 to k plus 1, so it's 1 over k plus 2 actually. So this is the smallest, and so the sum is larger than the smallest times the number of summons. And actually, so I think we are a bit better here than I thought. But anyway, okay, let's continue. And for this here, we know this is then smaller than L over 2k plus 1, 2k plus 2 right here now, I think. 2k plus 2. And on the right hand side, we can as well omit this term here because it's going to vanish anyway. So we are left with x0 minus x star squared. And that's it. So that's one trick how you get this 1 over k convergence right here. And I'm a bit confused because we get something better, right? We get it here with k plus 1 actually. You have to check, maybe I made a mistake in here, but I guess it's true. So the estimate should be like 2k plus 1, which is very tiny little better. But anyway, what's written up here is not false. Let's keep it like that. Okay, so that's already good news. The proximal gradient method is as good as the gradient method. Okay. So, and I think maybe it's time for the break already. So we're not at the half of the lecture anyways, but I think it's still good to have the break already right now. So after that we come to the acceleration. And then again, the proof of conversion of the acceleration and also the convergence rate is basically the same as the one for the accelerated gradient method, but we only do the simple case. Okay, but first 2-minute break, and so we'll be back here in 2 minutes. Okay, so actually I found the mistakes. I was just confused here. If we start the sum here at 1, of course we have the first hierarchy within the first sum here is f of x1, but here the first one is then 0, so 1 starting 1, and so this 1 here was corrected. Everything was fine. Okay. So good. Let's now do the acceleration. So I think this pen here is basically done, so let's continue in blue. Yeah, so acceleration works as well, and totally the same. So again, you do this xk, yk is xk plus alpha k, xk minus 1, and xk plus 1 is now the prox. hf xk minus h gradient of g xk. So it's exactly the same. And here, of course, you could do k here, but we don't do that in the proof, but you could. But it's a little harder to analyze. And again, we rewrite this, and now we do this a little more explicitly. Last time, the last lecture, the time was a little bit short, so we do it now. We rewrite this as xk is the prox of h, k, f, xk. Oh, sorry, this was between y and y, so sorry. And of course, here it's in yk minus 1 minus hk gradient of g of yk minus 1. And then we do, let's write it down a little bit different once again, with the variable uk, which we've actually seen before. And now this should be tk xk plus 1 minus tk xk minus 1. And then the next uk will be 1 minus 1 over tk plus 1 xk plus 1 over tk plus 1 uk. Okay, so this reparametrization, as we'll just we'll show in a second, gives exactly the same as this here, but it's a little bit nicer to analyze, because now while this is an extrapolation, so it really moves you forward, this here is a convex combination. So this uk lies between xk and xk minus 1, and the yk is again a convex combination. Right, it's again a convex combination between of these two guys. So it's looks kind of nicer to analyze, because then you have convex combinations. If you plug this in somewhere, you can do the usual convexity inequalities. Okay, let's show that this is actually the same. So this is now this time we formulate it as a lemma. So let's say this here and this here, this gets star like this, and this here gets 2 stars like this, and then say if alpha k is equal to tk here minus 1 divided by tk plus 1 in the index, then this and this produce the same xk. Okay. Yeah. So this is just basically it's just plugging in, but sometimes I myself get confused when I do so. We just plug plug the u in here and then see what's happening to the y. So the yk is then 1 minus 1 over tk plus 1 xk plus, and now we have here this uk will be that, so that gives us, so let's write it like 1 over tk plus 1 times tk xk plus 1 minus tk xk minus 1, and now we just collect everything. So how many xk's do we got? So we have 1 xk from here. Let's take this one. This is 1 xk. This has been from there, and then if we look at these two remaining xk's, they both have the factor 1 over tk plus 1. Actually, all the three quantities which are left have the factor 1 over tk plus 1. And so what do we have in front of the xk? The xk has a tk minus 1. Or the xk. But the factor in front of the xk minus 1 is also tk minus, it's 1 minus tk over tk plus 1. So that's a negative of the same. And that's already it, right? That was the full proof. So this here is then okay. Okay, so I could have done this last time, but the lecture last time was pretty full anyway. So, and now comes the same arguments for the proof of convergence of the accelerated gradient method. It's presented in a slightly different order, but anyway, so here comes the first proposition, which already gives what you need. So this is the same assumptions as before, only that now xk, uk, yk, according to this accelerated gradient scheme. Now we take h, k constant h as before, and as before between 0 and 1 over L. And then we have this estimate, and we've seen that before, it's tk plus 1 squared times f of xk plus 1 minus f star plus the sum, which is not telescoping here, k ti squared minus ti plus 1 squared plus ti times f of xi minus f star. And this is then smaller equal to 1 over 2h u0 minus x star squared minus uk plus 1 minus x star squared. And this should remind you of one of the results we had yesterday about the accelerated gradient method in the L-smooth case. Okay, so and since we know that already the proof is short, and it's it's again we can start from the same proposition, from the same inequality which made the proof of the accelerated gradient method work. So in this case, this is proposition 22.3.1 with again x is yk and x plus is xk plus 1. And of course in the special point z, this is a special point, so it's not uk, but it's 1 minus 1 over tk plus 1 times xk plus 1 over tk plus 1 times x star up here. So if we do that, we get f of xk plus 1 minus 1 over t instead of h again. Oh boy, 1 over 1 over 2t over 2h. So it's 1 over 2h xk plus 1 minus z, which is this guy here, so 1 minus 1 over tk plus 1 xk minus 1 over tk plus 1 x star squared is smaller than f of this is what is the z here, this goes also in here, plus 1 over 2h, and here we have yk minus again the same guy. I'm too lazy to write it down right now. And so one thing which we should observe here, that this is actually the same as f. I don't try anything here, but if you have a look at this yk minus this guy here, and then our definition of so in our iteration here, so this is the iteration which we use, and then you should recognize that yk minus this guys here actually is nothing else but 1 over 2h 1 over tk plus 1 times uk minus x star. Yes. This just use it from there. Okay, good. Yeah, and one more thing is we use convexity for this guy here because we have plugged in a convex combination, so this is then larger than smaller equal to 1 minus 1 over tk plus 1 of f of xk plus 1 over t. This last term we can put the t out here and get 1 over 2htk plus 1 squared uk minus x star squared. Okay, and also, yes, it remains to see something else which you also could have observed earlier on over here. Yes, so we can also write these two things here together as 1 over t k plus 1 times u k. There's some. Okay, so and then if we write that down once again a little bit more clearly, we get, let me see, how do we do it? And we also have this and this, yeah, so we get f of xk plus 1 minus f star minus 1 over tk plus 1 times f of xk minus f star. Like this, smaller equal, and then we oops, it almost fits. We collect this here and this on the right hand side, and we get uk minus x star squared minus oops, I there's something wrong with the k's and k plus 1s, unfortunately. Yeah, sure. So this here gives you k plus 1 actually. This here gives k plus 1 because we have an xk plus 1 here and an xk over there. And if you look at this line up there, this will get you an uk plus 1. So here it's in minus uk plus 1 minus x star squared. Okay, and then basically the same as before, we multiply by, so as before, I mean last lecture, multiply by t k plus 1 squared, sum up, and this proves the claim. So this is the same thing that we did last time, and I don't do it again in this detail. You get, yeah, this, that is it. Okay, so let's have a look at the inequality we just proved. And again, we see that this is all nice and good. What we only need to assume or ensure is that this ty squared plus ty plus 1 squared plus ti, that this is non-negative. And if we assume that, we get the same conversion as before. So as before, if ti minus ti plus 1 squared plus ti positive, then we get that f of x k plus 1 minus f star is smaller equal 1 over 2 h t k plus 1 squared, and then we can omit this this term here because it's going to vanish anyway, and this is just u0 minus x star squared, which would give us the desired conversion. Actually, again, x0 is equal to u0. Okay, and as before, with, for example, tk equal k plus 1 over 2. Yeah, gives us Theorem 22.7. So sorry, I didn't call. Maybe I should do something about it. So with this here, we get that f of x k plus 1 minus f star is small equal to L x0 minus x star squared over k plus 1. Now it's k plus 2. Why is k plus 2? Let me see. K plus 2 squared. Okay, so the proof is that's basically it's totally the same. So maybe I should prove this here because I omitted this last time. So first thing, it's that's the amazing result is the same as last time. It's as amazing. You get a method for a non-smooth optimization problem, but only a part of it has to be non-smooth but proximable. So the prox operator should be simple, and in the lab you see that at least for non-smooth things like the one norm, that is just no problem to apply the prox. You get this 1 over k squared convergence here. Okay, and maybe just as last thing, oops, my numeration here is kind of broken. Let's prove that this tk here actually works for that. And there's more typos, I guess. Sorry. Oopsie, I have to check for. Yeah, sheesh. It's also a typo in the theorem. Here, no, the typo in the proposition. That's again the typo. This is here. It has to be a plus 1, and this is actually what should have come out. So here, this was also here was a plus 1. Okay, so let's just check this that this here holds for this tk plus 1 over 2. So if we write that down, so check you check that ti minus ti plus 1 squared plus ti plus 1 is small equal for tk is k plus 1 over 2. Yeah. Okay. And again, is there so many typos? I forgot to copy. So here was a square and there was a square. So it was in the propositions was good. I just forgot it over here. So let's write that down with this guy here. And actually, we claim that it works for t plus a plus 1 over a. And then we'll see for which a this holds. So if we do that here, we get I plus a plus 1 over a squared minus 1 more than that. Yeah, just k plus 1. So this gives us just minus. There was a minus here. And then so there's a minus here. This gives us then k plus a over a squared plus k plus a over a, or let's do it with k's instead of i's. Okay, so if we now we see if we do that, we can factor out the 1 over a squared, and then here we have k plus a minus 1 squared minus k plus a squared plus, and this is just a times ka because k plus a because we have to multiply by a here. Okay. Now we expand the squares and see what cancels, and we expand it in the way that we get here k plus a squared minus k plus 2 times k plus a plus 1, and this is minus k plus a squared plus a k plus a. And you see that this goes away here, and what else do we get? We can put these two things together to get a minus 2 times k plus a, and again plus a. And so this is positive here if a larger than 2. So that we get that. So you can see we can do that here with this tk is equal to k plus a minus 1 if k is at least 2, and as you see before, a equals 2 is the best one when it comes to the upper bound. So tk equal k plus 1 over 2 is the best thing one can do. Okay, so that was it. So maybe let me just sort my things here. So let's take this once again and so so the conclusion of today is actually fairly simple. We now are able to solve problems like this with one smooth and a proximable term. Both have to be convex by the proximal gradient method, and it's basically a one-liner. You just have to implement the gradient and the prox map. So once you've done that, the rest is simple, and this always works and it always converges. So what you need is, you need to be able to calculate the gradient of g, you need to be able to calculate the prox of f, and you need one thing more, you need the Lipschitz constant of the gradient of g, because this gives you the step size here. You can take the step size 1 over L, and if you don't know the Lipschitz constant of the gradient of g, then and you just guess something, then you may see that the method does not converge. Then you say that the step size was too large. Then you can reduce step size as long as you see convergence of the method. This is kind of what you can practically do. But of course, the better thing to do is to calculate the Lipschitz constant in case you can, or at least estimate it from below. Okay, don't overestimate it. Okay, so this is the one thing. But apart from that, this is really straightforward to plug in. So you need to just do routines to evaluate these two things, and then you're done. And what is even more amazing is that if you do this slight twist here, maybe like this or like that, the amount of calculations you have to do is basically the same. So these are the expensive things. Otherwise, it's just calculating a few numbers and adding a few vectors, which is usually comparably cheap, and the method is just faster. So it's so simple that it's basically, in the convex case, you should basically just always do it. So the objective goes down much faster on average, not on average. So in the end, it goes down much faster, and you will see a payoff. Okay, so what if you now implement it? Which I guess you should in the lab. You be aware that if you plot f of xk here over k and start somewhere, that this method here will often lead to plots that look like this. So they go down and go up, but overall they go down. So, but if you see something like this, that's not a bug. It doesn't mean it has to be a bug. It can be just be real, because nobody proved that this method here will be a decent method actually. Or did we know? No, we didn't. It was like this for the gradient, for the simple gradient, proximal gradient method, but for the accelerated one, it's not true anymore. For the gradient method, we proved that it's actually a decent method here. That followed from here. The proximal gradient method is a decent method, but the accelerated proximal gradient method is not. So if you see something like this for the gradient implementation you did, then something's wrong with the implementation. But for the accelerated, that's fine. Okay, so that was it with the lectures for the course Convex Optimization. But the course is not over. There's an exercise class tomorrow afternoon and on Friday morning, and then there's the last exam on Friday afternoon. And of course, you may continue asking questions in chat or on campus wire. I will try to answer as fast as possible. So I hoped you learned something up to here, and you're going to learn even more until the end of the week, and that you can use what you've learned here in the future, no matter what comes here. And so for me it was a pleasure to unfortunately just meet you via chat, but that's better than nothing. And I hope maybe I meet some of you at some occasion in the future somewhere else. Okay, so all the best, and thanks for listening, and we keep in touch via chat, and see you then. Bye. And of course, for the others from Braunschweig, we continue next week with some more stuff in convex